So we're going to go over the intersection between like weighted averages and sort of like graphs, areas, displacements, and also just shortcuts that I have found to be useful in my life and that maybe you will as well. So we have an object here that is moving for 3 seconds. For the first 2 seconds, it is moving at a velocity of 2 meters per second, and the last second, it is moving at a velocity of 3 meters per second. Right. And so for part A, we simply have to find the average speed and the average velocity over the first 3 seconds. Easy enough. Now, the way that I like to think about it is sort of like weighted, like weights. I don't know if you're familiar with that concept, but let me just show you because I can't really explain it. So for the first 2 seconds, we have 2 instances of the object moving at 2 meters per second, and we have 1 instance of the object moving at 3 meters per second divided by the total time, which is 3. This is how I would go about this problem. Like right now, I'm technically calculating both the average velocity and the average speed, because speed is just going to be, speed is going to be connected to velocity in the sense that it will use the magnitude of the velocity we're dealing with. Right, so this is very obviously going to give us 4 plus 3 divided by 3, which is equal to 7/3, which is equal to 2.33 meters per second, which is going to be both our average speed, average S, and average velocity. It's going to be equal to that. Those are the answers for part A. Simple enough, right? Now, the thing that I found interesting was that, let's take a look at what we did here, right? We did 2 seconds pretty much times 2.0 meters per second, and we did 1 second times 3.0 meters per second, right? Let's take a look at our graph here. So if you can see, we calculate this area for the first 2 seconds. It's going to be 2 times 2, which is 4. And if we do the same thing and calculate the area for the final second, it's going to be 3 times 1, which is 3, right? Those are the areas for these portions here. Isn't that interesting? How these areas are connected to these numbers right here. Now, I don't know why. I'm going to be honest. I don't know why. But in my mind, it's sort of like a connection between taking weights to do the calculation and then the area beneath these graphs. Probably one of you has an explanation for it, but I don't. I just found it to be interesting, and I wanted to share. Cool. Now, for part B, we changed the situation so that, let's say that after 2 seconds, the object moved at negative 3 meters per second instead of positive 3, right? So our graph would look something like this. 2 seconds here, and then it just shifted over here for the last second, this being negative 3, and this being 2.0, right? Velocity versus time. It's going to be a similar calculation. I'm going to calculate the average speed first. That's going to be 2 instances of 2.0 meters per second plus 1 instance of the magnitude of the velocity for the last second, which is the magnitude of negative 3, divided by the total time. It's going to give you the same thing, 4 plus 3 divided by 7. The average speed is going to be the same, 2.33 meters per second, right? Of course, the answer changes when we calculate the average velocity, which is 2 instances of 2.0 meters per second plus 1 instance of negative 3.0 meters per second divided by the total time, which is going to equal 4 minus 3 divided by 3, which is equal to 0.33 meters per second, right? And again, that's because the area under this graph is now negative. It's negative 3 fighting against this positive 4 up here, right? Again, not too sure what the actual reasoning behind why, and like in my head, those like weights connect to the actual area under the graph, but I thought it was worthwhile to share, and I hope it was interesting to you as well.